Welcome to lecture number 6 on linear programming problems under this course on computational mathematics with Sage Math. In the last lecture, we looked at how to solve a linear programming problem using simplex method. We used our own user-defined function in order to solve linear programming problem step by step, and we also used an inbuilt function which is interactive LP problem. So let us continue with some more problems. So first thing we will do is we will store all the user-defined functions that we have created in a library called lplib, and we will save that as .py file, and let us import that all the functions that we have created from that library. So we are creating a module called lplib, and let us import all the functions. Let me show you what is this lplib. So that is let me see, this is the file. So you can see here what I have done is I have just copied the user-defined functions that was created inside this file, and I have saved it in lplib.py. So this is a pure Python file. Only one change I have made here that I would like to tell you. See, in the previous one we had used here infinity, but infinity is Sage variable. Here we have taken starting ratio as some large number, let us say 10 to the power 10. So that's the only change I have made, so that this you can use as Python program also. Right, now let us get back to the worksheet. So we start with a problem which is maximization problem. Maximize z is equal to x1 minus x2 plus 2x3 subjected to 2x1 minus x2 plus 3x3 less than equal to 5, x1 plus x2 minus x3 less than equal to 2, and minus x1 plus x2 minus x3 greater than equal to minus 2. Right. Now first we need to do is we need to convert this problem into standard linear programming problem, which is a minimization type objective function subjected to all the constraints which are equality constraint. All the right hand side should be non-negative and all the design variables should be non-negative. Now you can see here the third constraint here, the right hand side is negative, so we will multiply this entire constraint by minus 1. By doing so it will become x1 minus x2 plus x3 less than equal to 2. So now right hand side is positive and non-negative, and all the constraints are less than equal to, so each constraint will have to make it equality by adding slack variables. So again we will add slack variables, x4 in the first constraint, x5 in the second constraint, and x6 in the third constraint, and the objective function will become minimize minus z, which is minus x1 plus x2 minus 2x3 and plus 0 times x4, 0 times x5 plus 0 times x6. x4, x5, x6 are slack variables. Right. So let us first create this matrix A as we did in the last problem. The matrix A will be the coefficient matrix along with the right hand side. The last column will be the right hand side, and the bottom column, that is the bottom row, that is the last row, will correspond to the reduced cost coefficient, or Cj minus Zj. So you can see here the last row here is minus 1, 1, minus 2, 0, 0, 0, and this is the value of the objective function at this stage, which is 0. So we are starting with initial basic feasible solution, which is x1 is equal to 5, x5 is equal to 3, and x6 is equal to 2, and x1, x2, x3 will be non-basic variables. x4, x5, x6 are basic variables. So again let us write this in a tabular form by adding the top row and the left hand side, the basic variables x4, x5, x6, the header row along with the right hand side, and we create a table of this. So that is your just one second, we have not executed A, so after that let me execute this. So this is your initial simplex table, right? Again you can see here the reduced cost coefficient row contains negative entry. Therefore, this particular solution, basic feasible solution, is not optimal at this stage. So we will have to update this table. That means we need to bring one of the non-basic variable to basic variable, and one of the basic variable has to be pushed out of the basic variables. So how do we do that? So first we will find out what will be the incoming variable by calling the function pivot column. Again, here the number of variables is 6. So let us call this, and in this case it says that x3 is incoming. So x3, you can see here that this is the most negative value of the reduced cost coefficient. So that column is incoming column. Incoming variable is x3. Now let us decide what is outgoing variable. So outgoing variable will be obtained by calling this function pivot row and a comma q. Q is incoming variable. So when we do that, it says that x4 is outgoing variable, and you can see here what in this case we decided x3 is incoming. So there are only two positive coefficient, 3 and 1. So if I look at the ratio 5 upon 3, and the other one is 2 upon 1. So this is 2 and this is 5 by 3, which is smaller. Therefore x4 is outgoing variable and x3 is incoming variable. Having decided incoming and outgoing variables, now let us update the basic variables. So x4 will be replaced by x3, and then we will update the simplex table by pivoting, and then let us update this simplex table. So now you can see here, after we have updated, in this case we are getting the solution in one step, because all the reduced cost coefficients have become non-negative. Therefore this is an optimal solution, and that we obtained in one step itself. So in this case, what is the solution? You see that basic variables are x3, x5, x6. So therefore x2 and x1 are non-basic variables, so they will take value 0. So x1 is 0, x2 is 0, x3 will be 5 by 3, and the value of the objective function is 10 by 3. So that is how we can solve using our inbuilt functions, pivot row, pivot call, and pivoting. Now let us look at the same thing again. Let us solve the same problem using step by step using inbuilt function. So how do we do that? So we'll have to define the coefficient matrix A as a list of row, the right hand side B, and the coefficient of the objective function C, and then define the problem in P, which is interactive LP problem with input A, B, C, then the variables. The problem type is again maximization. Constraint type are all less than equal to, variable type are all non-negative, and then convert this into standard form, and let us ask it to show what is the problem it has formulated. So you can see here the problem is exactly the same as what we started with. Now how do we solve this? So we'll have to just say p dot run simplex method, and when you say p dot run simplex method, you can see here in this case when we have used the inbuilt simplex method, it is using more than one step. What answer we got in one step, in this case it is taking more steps. So you see that this is a problem in which you have got the solution in one step when we used our algorithm, but in this case the inbuilt function takes more steps. So there is no actually way in which we can decide that if I take this particular incoming variable and this outgoing variable, then it will require lesser number of steps. When we take most negative reduced cost coefficient, it is just a greedy approach, right? So this is your initial basic simplex table, and this is the incoming variable, and this is x6 is outgoing variable. So after that, so x1 is entering, x6 is leaving, and the next step you have x3 is entering variable and x4 is outgoing variable, and then in the next step you have x1 is entering variable, x6 is outgoing variable. So you got the and then this is what you have. So the solution which you have got is x3 is equal to 5 by 3, and x5 is 14 by 3, x6 is 1 by 3. Therefore, the solution is at 0, 0, 5 by 3, and the minimum value of the objective function or the maximum value of the objective function is 10 by 3. Right. So that is how we can solve using inbuilt method called run_simplex, and also we have used our own step-by-step user-defined function. Right. So and in this case you can see here this problem is kind of having only one variable non-zero in the solution. Right. Okay. Anyway, so and in case, as I said in the previous class, in case this particular p.run.simplex method does not give you the output or does not display the output in proper format, maybe you can try with this particular code. This may help. Right. I'm not sure about that, but you can try it out. This might help. Okay. Fine. Let us look at one more problem. So this is maximize two variable problem, that is 2x1 plus x3 subjected to this three constraints. Again, all these constraints are less than equal to. Okay, so let us try to solve this problem. So again, we will first convert this problem into a standard form, that is minimize negative of z subjected to all the equality constraints. So again here 4 variables are introduced with respect to each less than equal to constraints x4, x5 and x6, and then we will define the matrix A. We will create the initial simplex table. We will create the initial simplex table, and then again we will update this. We will find out incoming variable and outgoing variable by calling the two functions pivot call. So in this case x1 is incoming, and that is what you can see here. This is most negative. So x1 is incoming. Next we will decide what is the outgoing variable. So outgoing variable is x4. That's because the ratio here is, this is the only positive one, so the ratio is 5. So therefore x4 becomes outgoing variable. And once you have decided incoming variable, outgoing variable, then you can update the basic variables and pivot, so that you will get this pivot, the updated simplex table. And again, when we update, there is another negative reduced cost coefficient. So again, this problem, this basic feasible solution is not optimal. So again, let us find out outgoing variable. In this case is x2. That is what you can see here. The second column has negative reduced cost coefficient. Therefore, x2 will be incoming variable, and then we will decide outgoing variable, and in this case x6 is outgoing variable. So that is what you can see here, because the other two ratios, other two coefficients here are negative. This is only the positive one, so this will be x6 will be outgoing variable. Now again, update the basic variables and update the apply pivoting, that is apply elementary row operation, and then write down the basic the simplex table, update the simplex table. Now in this case again there is one negative corresponding to x3, so we will further update the simplex table by finding the pivot call. So here x3 is incoming, x3 is incoming. Now in this case you can see here, this is x3 is incoming, but however this there is no positive coefficient in this particular incoming column. Therefore this problem is unbounded. So if I try to find out what is a pivot row, then it says that this list indices must be integer or slice not. So it has already it is giving you an error because it cannot find any positive coefficient. Right. So this problem is unbounded. This problem is unbounded. This is an example of unbounded problem. Right. If you try to solve this again using inbuilt function LP, interactive LP program, again you can see here this problem is unbounded. Let us look at one more problem. This is maximize 20x1 plus 30x2 subjected to 6x1 plus 9x2 less than equal to 100 and 2x1 plus x2 less than equal to 20. So again, first we'll convert this problem into a standard form and then create initial basic simplex table. Again, in this case, both the coefficients, both the constants are less than equal to, therefore we need to introduce two slack variables, namely x3 and x4. So that first row is going to become 6910 and the right hand side is 100. Second row will become 2101 and then 20, and then the coefficient will become the minimization type, which is negative of 20, negative of 30, 0, 0, that is the value of the objective function. Okay. Now let us again update this, because this particular solution is not optimal. So this is the reduced cost coefficient. You have negative 20, negative 30. So we will choose x2 as incoming variable, so that we can obtain using pivot call. So when I say pivot call, it says that x2 is incoming, and let us find out outgoing row, that is outgoing variable, that is x3, because the ratio, if you look at here in terms of x2, this column, so 100 by 9 and 20 by 1, so therefore 100 by 9 is the smallest, so x3 is outgoing. Right. Now let us interchange the basic variables or update the basic variables and apply pivoting on A, P, comma Q, and then write down the revised simplex method. So in this case, you see here the revised simplex method gives you, this is again the optimal solution, because all the reduced coefficients have become non-negative. The value of the objective function is 1000 divided by 3, and here what are the basic variables? x2 and x4 are basic variables. However, if you look at the non-basic variables, what are the non-basic variables? Non-basic variables are x1 and x3. But if you look at the coefficient of one of the non-basic variable, for example x1, that coefficient is 0. So that is a case of alternate solution. That's the case of alternate solution, right? In this case, that is what I have written here. x1 is equal to 0 and x2 is equal to 100 by 9 is a basic feasible solution with optimal value is 1000 by 3. However, the reduced cost coefficient corresponding to non-basic variable x1 is 0. This is a case of alternate solution. So in this case, if you try to, for example, instead of choosing the incoming variable to begin with as x2, if you start with x1 in the first step, you might get another alternate solution. However, let us solve this using inbuilt function, or let us try different incoming and outgoing variables. So this time I will not use pivot row, pivot column, but we will take our own incoming and outgoing variables. So here P is 1, that means we are taking x3, we are taking x3 as outgoing variable, and we are taking x1 as incoming variable. So this is the reduced cost coefficient that we are taking. So if I update this this table, now you can see here, now this is the negative one. So again we have to update. So we will take P is equal to 0, that is x3 is outgoing and x2 will be incoming. And when we apply this and then update, this is the solution we have got, which says that x1 is equal to 20 by 3 and x2 is equal to 20 by 10, and again the value of the objective function is going to be 1000 by 3. So this is an alternate solution. So you got more than one solution in this case, right? If you fine. So that is how you can find out whether a linear programming problem is unbounded or it has an alternate solution. Let me again reiterate. When the problem is unbounded, in case you have found out an incoming variable from the non-basic variable and look at the column corresponding to that incoming variable, in case all the entries in that particular column are negative or less than equal to 0, then that is a case of unbounded linear programming problem. And in case you have a basic feasible solution, optimal basic feasible solution, in which the reduced cost coefficient, the cost coefficient corresponding to non-basic variable is 0, then you have a case of alternate solution, because that what it means is that in case that reduced coefficient is 0, then that can come in the basic row, and that will not alter the value of the objective function. So that is why you have alternate solution, right? And we have seen what it means geometrically. So if you try to solve this problem geometrically, as we did in the last class, you will realize that this problem will have alternate solution, right? So now let us look at how we can solve linear programming problem using mixed integer linear program. As I said earlier, this interactive LP problem is basically meant for educational purpose. Though it gives you step-by-step simplex method, but when you want to solve the problem more efficiently, or if you have a problem which is a bigger problem involving more number of variables, etc., it is better to use mixed integer linear program. So what is this mixed integer linear program? How do we make use of it? So again, let us start with the problem which we have solved earlier, namely this maximize 2x1 plus 3x2 plus 3x3 subjected to these three constraints. We have already solved this problem using step-by-step method and also using interactive LP problem. Okay, so first we will define this problem. So how do we define? We will call mixed integer linear program, and we will store this in variable small p, and here we will mention what is the problem type, objective function type, which is maximization type. So we'll say maximization equal to true. In case this problem is minimization, we'll say that maximization equal to false. And then it has various options to use solver, and it can use a solver which is called GLPK. So let us execute this. And what is GLPK solver? It is what is called GNU Linear Programming Kit. Okay, this GLPK is GNU Linear Programming Kit. It is a package which is intended for solving large-scale linear programming problem, including mixed integer programming problem. I have already defined what is meaning of mixed integer programming problem, where you have some design variables which are real, non-negative, and some design variables are integers, right? And you can also solve other problems as well. This package is written in ANSI C, and it is organized in the form of callable library. Say for example, we created lpp lib.py, and from which we are able to call all these functions. So it is something similar to that. Okay, so let us look at how we can use this particular package, mixed integer linear program, and in that GLPK package, right? Okay, so first we have defined this problem. So that's the basic problem definition that we have stored in P. Now by default, in this case, if you create, the default variables will be P0, P1, P2, P3, etc. Right? P0 is, you can think of as the first variable. So index starts with 0. Now instead of writing this as P0, P1, P2 and so on, let us write this as X0, X1, X2, X3, because those are the variables that we have, right? We have X1, X2, X3, but X1 will be considered as first in the list, which will be X box 0 or X of 0, right? So let us redefine this into X. And so how do we do that? We have to say P dot new variable, and we'll also mention that non-negative equal to true. That means all the design variables will be non-negative by default, right? So if the minimum value will be 0, maximum value will be infinite, right? Now what do? We will have to set objective function and each constraint. So what is the objective function here? 2x1 plus 3x2 plus 3x3. So that we will add. So we'll say P dot set objective, and inside the round bracket you write this objective function, which is 2 times x of 0 x of 0 is nothing but x1, 3 times x of 1 plus 3 times x of 2. So that is how you set objective function. Next we have to set constraints. So all these 3 constraints you can set using this what is called p dot add constraints, and inside the round bracket you write whatever is the constraint. So first constraint was 3 times x0 plus 2 times x1 less than equal to 60. So you can write less than equal to 60, or you could write max is equal to 60, because the left hand side value of this constraint for x0 is 0 and x1 is also 0, so the minimum value will always be 0, and you have to, all we need to say is maximum value is equal to 60 or whatever you have. So either you can write this in terms of inequality or write down the left hand side of the constraint and say what is the maximum value. Okay, so these are the 3 constraints. Let us add these 3 constraints, and then once you have added these 3 constraints, let us ask P to show what is the problem it has formulated. So when I say P dot show, now you can see here the problem is maximize 2 times x0 plus 3 times x1 plus 3 times x2 subject to the constraints. The first one is 3x1 x0 plus 2x1 less than equal to 60, and so on. And this x1, x2 and x0, they are all continuous variables. Minimum value is 0 and maximum value is plus infinity. This plus OO means plus infinity. Right, so that is how it has formulated this problem. Now how do we solve this problem? So in this case, if you recall, for 2 variable problems, we were able to plot the constraint set, and here this is problem is 3 variables. So in principle, Sage can also plot the constraint set for 3 variables. Let us see how we can do it. So one, you can apply p dot polyhedron, and when you apply p dot polyhedron, this will give you the constraint set in terms of what is called polyhedron, and it says that it is a 3-dimensional polyhedron in over some field, which is also known as convex hull, and it has got 8 vertices. It has got 8 vertices. So there are 8 corners. So there are 8 possible basic feasible solutions from which you can get the optimal basic feasible solution. Now you can also plot this. How do we plot this? We'll say p dot polyhedron dot plot, and let me execute this, and in this case you will see 3-dimensional polyhedron. So this is what you have. Let me rotate this and so. Right, so you can see here there are 8 vertices. What are the 8 vertices? 1 here, 2, 3, 4, 5, 6, 7, and there will be 1 which is somewhere here, 8. So there are 8 vertices or 8 corner. This is the constraint set. So each surface will be representing the equality of each of this constraint. Right. So this is how you can plot the constraint set for 3 variable problems. That is quite nice feature in Sage Math. Now let us look at how we can solve this problem. So the problem which we have defined in P, now if you simply say P dot solve, then it will give you, in case it has a solution, it will give you what is the value of the objective function, which is 70. The objective function is 70, and let us find out what are the actual values of the constraint, what are the values of the variables at which this optimal occurs, and this can be obtained as p dot get values. So it gives you values in terms of dictionary. So it says that the 0th coefficient, that is x0, value is 8, and x1 is 18 and x2 is 0. So that actually means that x1 will be 8, x2 is 18 and x3 is 0, and that is what we obtain when we solve the same problem using our own inbuilt function and also using interactive LP problem. So that is how we can make use of this particular function, which is called mixed integer linear program, and this is actually more efficient way of solving linear programming problem, and it will work even for problem which are mixed integer programming problem as well. Right, so we will make use of this many more times in the future. Now let me leave you some exercises. So you should try these exercises. The first is use simplex method to maximize this function. So in all these problems, I expect you to solve using the inbuilt function that we have using interactive LP solve, and other one which we used just now, mixed linear programming problem, and also using our user defined function, so that you become comfortable using all these three ways of solving. Of course, the last two problem here, the one problem is of having alternate solution, and this problem is unbounded, so you have to show that this problem is unbounded, right? So these are the few problems that you can try to solve. As I said, in all these problems you should apply the three methods, and in case you have two variable problem, you can even try graphical methods. Okay, so thank you very much. Next time we will look at how we can modify simplex method and maybe use another method. So one of the difficulties that we have in simplex method is to start the initial simplex table. That means we need initial basic feasible solution, which is not always possible to guess. Whatever problems that we have looked at, in these cases we had some in all these cases we had constraints which were less than equal to type, so we could just introduce slack variables, and that gave rise to basic feasible solution, but that need not be the case always. So we will look at in the next class how we can overcome these difficulties. Thank you very much.